Hello friends, so here we are with another question on KVL and KCL application. So here we have this circuit diagram and there are three branch currents that have been assigned in this circuit: I1, I2, I3. We have been asked to find the values of these currents. Okay, so basic application of KVL and KCL, it's all about that. Okay, basic understanding of circuit and KVL and KCL application. So here we have redrawn the circuit, and what we have done is we have assigned, we have named each node so that it will be easier to identify when we apply a particular loop or KCL equation. We can identify the node where we have applied A, B, C, D, E, F. Okay. So first let us assign the branch currents. Okay, at node B, node B here. So here current I1 is flowing, I2 has gone away, so this current will be obviously I1 minus I2. Okay, at node C, at node C, I1 minus I2, just a minute. So here it is I3. It will be easier if we move from this side. Okay, it will be easier. So I3 is flowing like this. Before attacking here, let's proceed from this known side. Okay, here it is I3. Here also I3 current is flowing. Here it is 4 ampere current. So this one will be I3 plus 4. Okay. So at node C we have I3 plus 4 approaching, 9 ampere approaching, and I1 minus I2 approaching. So the total current here will be the sum of each of these currents. Okay, every current here is approaching, 9 ampere is approaching, I1 minus I2 is approaching, I3 plus 4 is approaching. So this current will be I1 minus I2, this one, plus 9 ampere, this one, plus I3 plus 4. So that's the reason why I approached it from this side, because this current was not known, the current in this branch. Okay, so you're clear about it. First, these are the given currents I1, I2, I3. We applied KCL at each node to get the currents in the branches that were not, it was not there, it was unknown. We got them. Now it's all about application of KVL. Now here another interesting thing is happening. This current here is I1 minus I2 plus 9 plus I3 plus I4. But here also it is I1, the same current in that. So first important equation, interesting one, will be this. I1 is equal to I1 minus I2 plus 9 plus I3 plus I4. So obviously here this is 9 plus 4. Okay, this is not that, it is 9 plus 4, not I3 plus I4, it is 4. This was I3 plus 4, not I4. By mistake I have written I4 here and here. I3 plus 4 it is. By mistake I have written I4, it is 4 because of this 4 ampere, and here also it is 4. Okay, please rectify it. So here this will get cancelled. That implies the equation will be I2 minus I3 brought to the left hand side is equal to 9 plus 4, which is equal to 13 ampere. That is the first equation that we will get. Okay, this. Then let's say we will apply KVL in this loop A, B, C, A. So for that we have to assign the polarities, plus, minus. Let us assign the other polarities as well at a time. Here it is flowing in this side, so it will be plus, minus. See, I3 is flowing in this direction from right to left, that's why polarity is like this. In all the other cases it is left to right, so that's why in this case. So we are applying KVL in the loop A, B, C and then back to A, in this loop, this one, okay, this loop. So here the KVL equation in loop A, B, C, A, that is minus 12I1 minus 8 into I1 minus I2 is equal to 0. That implies minus 12I1 minus 8I1 plus 8I2 is equal to 0. That implies minus 20I1 plus 8I2 is equal to 0. This is another important equation. So let us name them. Let's say this is equation number 1, this is equation number 2. Okay. So now let us apply another KVL. It will be a very interesting one. So let us say we apply this KVL here in this entire path. Deliberately I have taken this figure as separate. We will be applying the KVL in this direction. From A we will start, okay. Please pay attention here. KVL can be applied from any point to the same point, traversing any path such that it forms a closed loop, okay, like that, and no point should be traversed more than once. So here we are applying the KVL, the second KVL we are applying. We are starting at A, okay, we are starting at A. Then we are moving in this direction to B, then to D, then to F, then to E, then to C, then back to A. This is the direction of the KVL path. This is the direction of the KVL path. KVL path A, B, D, F, E, C, A. Okay. So here if we apply KVL in this direction, then the equation will be like this. So the current here is this much, here it is I3 and here it is I1. So the KVL equation here will be minus 12I1 minus 16I3, that is equal to 0. Okay, minus 12I1 minus 16I3 is equal to 0. See, such a long KVL path, long and complex KVL path, but such a simple equation, because in the other branches there is no resistance involved, so no voltage drop. Only these two resistors are encountered, and these are the voltage drops because of the currents flowing. I1 is flowing through 12, I3 is flowing through 16 ohm, so that's why minus 12I1 minus 16I3 is equal to 0. So we have got three equations. I2 minus I3 is equal to 13 ampere, minus 20I1 plus 8I2 is equal to 0, and minus 12I1 minus 16I3 is equal to 0. So let us put okay, equation 1 and 2. Okay, we'll put equation 1 and 2. So I2 is 13 plus I3, this one. I2 is equal to 13 plus I3 from equation 1. We put that in equation 2, that is minus 20 I1 plus this one plus 8. Instead of I2 we'll write 13 plus I3 is equal to 0. That implies minus 20 I1 plus 8 I3 plus 104 is equal to 0. That implies minus 20 I1 plus 8 I3 equals to minus 104. So this is the fourth equation that we have got. Fourth equation, minus 20 I1 plus 8 I3 is equal to minus 104. Now see, if you compare equation 4 and equation 3, you will see that both are in terms of I1 and I3. Both are in terms of I1 and I3. Here we have 8 I3, here we have minus 16 I3. So if we multiply equation 4 with 2, if we multiply equation 4 with 2, we will get, multiplying equation 4 with 2, we get minus 40 I1 plus 16 I3 equals to minus 208, and then we add this equation 3, minus 12 I1 minus 16 I3 is equal to 0. We add it. So then this gets cancelled. Plus 16 I3 minus 16 I3 gets cancelled, and we get minus 52 I1 is equal to minus 208. Okay, minus 52 I1 is equal to minus 208. So I1 is equal to 208 by 52, which is equal to 4 ampere. I1 is equal to 4 ampere. First current we have got, I1 is equal to 4 ampere. Then there is some relationship between I1 and I2, something we have got here. Here we can use any of these relationships to get I2. We can substitute here. Okay, in substituting this value I1 here, we get, if we substitute I1 here, minus 20 into 4 plus 8 I2 is equal to 0. That implies 8 I2 is equal to 80. That implies I2 is equal to 80 by 8, which is equal to 10 ampere. So we have got I2. I2 is equal to 10 ampere. I1 equals to 4 ampere. We have substituted in equation 2. Okay, we have substituted I1 4, then we got the value of I2. Then we substitute the value of I2 in equation 1. I2 minus I3 is equal to 13 ampere. So I3, 10 minus I3 is equal to 13 ampere. I2 minus I3 is 13 ampere. That implies I3 is equal to 10 minus 13, which is equal to minus 3 ampere. So I3 is equal to minus 3 ampere. So don't be be scared about the negative sign that has come. It only means that the magnitude of the current which is given in the question, that is 3 ampere, but the direction is actually opposite to the arrowhead which is given in the question. I3 is equal to minus 3 ampere. It only means magnitude is this 3, but direction is in the opposite to the one assigned in the question. It is actually in this direction. This is 3 ampere, but if we take this direction, it will be minus 3 ampere. So just the direction is opposite. All the other I1, I2, they are the same. I1 is equal to 4 ampere in this direction and I2 is 10 ampere in this direction. Only the direction of I3 is opposite to the one given in the question. Okay, so this is an interesting question here which involved a very good understanding of Kirchhoff's current law, which was applied in various places. Then KVL, an interesting application of KVL here, which led to a very simple equation but a very long complex path, but a simple equation. So it was a very good question. So here we have discussed another question related to application of KVL and KCL. Hello friends, so here we are with another question on KVL and KCL application. So here is the circuit diagram which we have, and we have been asked to find the currents in all these resistor branches, okay, current flowing through each of these resistors, okay. So at each junction, at each node, we have either a current approaching or a current flowing away, okay, either it's entering or exiting that node. So that is interesting. So we have been asked to find the current. So it is again the main principle that will be used here is KCL, and then we'll be using KVL to find the current value. So here first what we'll do is that, let's say we start with this 0.02 ohm resistor branch, and let's say we assign a current direction like this, okay, yes, we assign a current direction like this, and let's call it X, okay, we call it X ampere is flowing. So here also it is X at this node, okay. Here 30 ampere is flowing away, it is exiting the node. So here the current will be, let's call it, write it here, it will be X minus 30 ampere, because here this node current X is approaching, flowing towards, 30 ampere is leaving, so it will be X minus 30. Again, pay attention to this node. So first of all, let us name these nodes, okay, let us name these nodes, it will be helpful. Let's call it A, B, C, D, E, F, this, okay. So here it is like this, and here at node E 70 ampere is approaching, entering, X minus 30 is approaching, 70 ampere is also approaching. So it will be the sum X minus 30 plus 70, which will be X plus 40, X plus 40 flowing through this 0.01 ohm resistor. Then again at node D, here X plus 40 is entering, 120 is exiting. So this current will be X plus 40 minus 120, which is X minus 80, this. Again at node C, X minus 80 is entering the node C, 60 ampere is also entering the node C. So here it will be X minus 80 plus 60, which will be X minus 20, this one, X minus 20, flowing through this 0.01 ohm branch, BC branch. Then here X minus 20 is entering the node B, 60 ampere is flowing away from node P. So here it will be X minus 20 plus 60, which is equal to, sorry, X minus 20 minus 60, sorry, not plus 60, minus 60, because it is flowing away. X minus 20 minus 60, okay, it will be X minus 80. This will be x minus 80. So see, it is satisfying. Here at node A, x minus 80 is flowing into 80 ampere is flowing into node A, x minus 80 plus 80, that is x. So everything is satisfying. So we have assigned the branch currents, taking one current as x, determined all the other currents through basic application of KCL. Now we will assign the polarities. So here the polarity will be plus minus, here also it is plus minus, current always flows from positive to negative, here also it will be plus minus, here also it will be plus minus, here also it will be plus minus, here also it will be plus minus. Now all we have to do is apply KVL in this closed loop starting from A to F, like this. We will apply KVL. Okay, here KVL path. This is the KVL path. So here it will be, if we apply KVL in this closed path, starting from, let's say F, we start from F, it will be everything positive will come. We are starting from F. We are starting from F and then we'll go back to F, okay, F to F. So here it will be 0.02 multiplied with x plus 0.02 multiplied with x minus 80 plus 0.01 multiplied with x minus 20 plus 0.03 into x minus 80 plus 0.01 into x plus 40 plus 0.01 into x minus 30. This is the KVL equation. This is the KVL equation. Now if we simplify it, it will be 0.02x plus 0.02x minus 1.6, this one 0.02 into 80 plus 0.01x minus, it will be 0.2, it will be 0.2 plus 0.03x minus, it will be 2.4, 0.03 into 80, then plus 0.01x, let's take it a little bit downwards so that we have some space. It was okay, 2.4, then 0.01x plus, it will be 0.4, okay, 0.01 into 40, then 0.01x minus 0.3. Okay, so when we add everything, bringing x terms with coefficient x terms on one side and all the constants on the other side, will be 0.1x minus 4.1 is equal to 0. That implies 0.1x is equal to 4.1. That implies x is equal to 4.1 by 0.1, which is equal to 41 ampere. X is equal to 41 ampere. This x. Which is the current flowing through this AF branch. Okay, so if we name it A, B, C, D, So this current we got as 41 ampere. This current AF 41 ampere. Current flowing through IAF we got. IAF is equal to X, which is equal to 41 ampere. Now current flowing through FE branch, this is X minus 30. FE branch is X minus 30, so it will be IFE is equal to X minus 30, which is equal to 41 minus 30, which will be 11 ampere. IFE is 11 ampere, so this is 11 ampere. Then current flowing through ED is X plus 40, X plus 40, so that will be here IED X plus 40, which is equal to 41 plus 40, which is equal to 81 ampere. This current is 81 ampere. Then here current flowing through DC is X minus 80. Current flowing through DC is X minus 80, which is equal to 41 minus 80, so that will be minus 39 amperes. So here what minus 39 means is that the direction which we assumed, okay, everything about assumption, we can assume current direction any direction, but here our assumption was wrong, okay, it is actually in the opposite direction. So it is like this, it is like this, current is flowing in this direction, which is 39 ampere. Magnitude is right, but direction is opposite. See here 81 plus 39, it is getting 120. So it is actually ICD, the current direction is from C to D, not D to C, that is equal to 39 ampere. Okay, this is important. Then current CB is X minus 20. Current CB, ICB is X minus 20. So that will be 41 minus 20, which is equal to 21 ampere. 41 minus 20 is equal to 21 ampere. So this is 21 ampere. ICB is equal to 21 ampere. Then we have IBA X minus 80. IBA is X minus 80. Again it will be the same thing, it will come negative. X minus 80. 41 minus 80 is equal to 39 ampere minus 39 ampere. So it will be the opposite. It will be not BA but A to B, this direction. This direction it will be like this, 39 ampere. See here we assumed it moving from B to A, but it came minus 39, magnitude is right. So it is actually from A to B, I A to B, that is equal to 39 ampere. So this is 39 ampere. So here we have got all the branch currents. A to B is 39, B to actually it is C to B, which is 21, then C to D is 39, E to D 81 ampere, F to E 11 ampere, A to F 41 ampere. So this is the result. Okay, so again it was first application of Kirchhoff's current law at each node to find out the branch currents in terms of X, then application of KVL in this closed loop to get this equation, then just basic mathematics plus minus that, and we got all the currents in the individual branches.